How's it going, guys? In this video I just want to do a really quick thermochemistry topic review just to kind of cover all of the most important details of this chapter. I'm going to go into detail in each of these in their own videos, but I wanted to kind of clump all the major concepts into one just for review purposes. So first of all, in thermochemistry, one of the first things you do is calculating heat through phase changes, and whenever you're doing that, this chart is your best friend. Basically, this kind of covers everything, and it seems a little bit complex, but if you watch the video, I draw it out. Basically, as temperature increases, regardless of the element, so that's why I didn't actually put numbers here. This could be water, aluminum, copper, zinc, whatever. On the slopes, you have the states of matter, and then on the plateaus is kind of the transitional areas. And so at the bottom here, you have solid. Then you have liquid in the middle and gas at the top as it increases in temperature. And then obviously you have freezing this way, melting this way, condensation this way, evaporation that way. And then you basically, whenever you're solving these problems, you're moving from solid to liquid or liquid to solid or gas or whatever. You're going to use different formulas depending on which part of the line that you're on. So for any of the slopes, you're going to use this formula here. Q equals m times c times delta T. So that's going to be mass times the specific heat or the heat cap times the delta T, which is usually in Kelvin. Then on any of these flat areas, you're going to use one of these two formulas. If it's the lower of the two between solid and liquid, you use the heat of fusion, so Q equals n times heat of fusion. And then on the top, you're going to use Q equals n times the heat of vaporization. And then the other ones, these are really rare that you're going to need to know this, but solid to gas, if it's a transition from solid to gas, that's sublimation, and from gas to solid is deposition. And the most important thing I think here is probably the fact that when you're moving from the right to the left, it's an endothermic reaction, and when you're moving from the left to the right, it's exothermic. So that kind of covers everything that you probably likely need to know about that. The next probably topic is calculating specific heat. And that pretty much you're always going to use this, the Q equals MC triangle T. And then from there you can also use this, which is M of A times C of A times triangle T of A is equal to M of B C of B. It kind of reminds me of one of the ideal gas laws. Here we go. So basically you're comparing the two, and the reason that you can do this is because heat lost by A equals heat gained by B. And obviously A and B you can substitute for anything, but in these cases you can think of it also as the system versus the surroundings. And if it's going in from the surroundings, heat, the surrounding is losing and the system is gaining. You can kind of look at it as that kind of perspective, and we can set these two as equal. That will help in those types of problems from there. And then in the next thing that you're usually going to have to do is enthalpy change calculations, and then for that, they're mostly algebra, to be honest, except for you're going to use a few formulas, like for instance D equals M over V, or I showed in one of the videos we did, I think it was M equals dV. And you're going to have to do some of those. PV equals nRT might rear its head again, but mostly you're going to have either this formula here, or you're going to have the enthalpy is equal to negative heat over moles. And in that case, there's some formulas associated with calculating moles, but really be careful that you make sure that you take heat and then add the negative sign, because if you already have a negative heat to begin with, your heat is then going to become positive, basically. Even though technically speaking, like I've said in other videos, this is just for calculation purposes, but heat shouldn't really in reality be negative. So from there we're going to have the biggest topic of thermochemistry that's covered in general chemistry too. We have the ways to find delta H, and there's 4 ways, and each of them is different, obviously, but they can be substituted into different types of problems. So for calorimetry, basically what we have is you mix this with this, or you put this metal into this water or something like that. Basically, for most of the calorimetry problems, we're calculating enthalpy per mole of one of the compounds that's involved in the reaction. And for that, again, we just use these same formulas down here. I don't think that there's anything too unique about those problems other than basically a lot of times we're going to have the assumption that this is where you get a lot of the problems that list assume the density is equal to 1 gram per ml, and say you have 100 ml. So now you have right there, you can basically, if you have the volume, you can calculate also the number of grams in terms of using this formula right there. So that's calorimetry. It's not too bad. Hess's law is the next one we have. Basically, for Hess's law, regardless of the multiple stages of steps of a reaction, the total enthalpy change for the reaction is the sum of all changes. So like I say in the video, that's pretty wordy, but it's actually pretty straightforward. Basically, you just add them up. You add the segments of different reactions that add to the reaction that you're trying to figure out the enthalpy for. And those are covered, like I said, in detail in another video. I think that they're probably one of the easier of all of them in terms of making mistakes, but they're just, you just have to, it's like a puzzle, you just have to work through them. Now for enthalpies of formation, we just have this formula here, which we use, and it seems a little bit complex, but basically you're taking the sum of the products, so the sum of the enthalpies of formation of the products, and then subtracting the sum of the enthalpy of formation of the reactants. And then that's how you're going to find those answers. And for these, I think they're pretty straightforward. Basically, you're going to just want to be really careful about those brackets because you have the outer brackets and then minus. Sometimes you only have one, sometimes you have two, but just make sure that you're not subtracting where you shouldn't be subtracting, basically. And then for the final one, for bond enthalpies, I think the most important factor here is learning how to draw out. For example, if they say C2H4, you don't want to draw that as I'm sorry, that would have been H6, but you wouldn't want to draw it without the double bond in the middle. Basically, you want to make sure that for the carbons, the octet is filled. They have 4 bonds, or whatever they have, either 4 bonds or they have a lone pair or something like that. But sorry about that, was kind of a bad example. Another one would be, for instance, if you had CH3Cl, you want to know that it's going to be the 3 H's are coming off the C, and the C's bond to the Cl, not like somewhere in the middle or something else, some other variation. Those might seem like pretty obvious examples, but like another one is CO2. Like I think a lot of people would just write CO2 as though it was, I don't know, and then you add these, and I'm not sure exactly if many people would have known that, but I think it's just if you can get the hang of drawing out the molecules, then that's the best way I think to increase your accuracy, because other than knowing which bonds are where in the basic structure of the molecule in theory, then that's something that will, I think, go a long way towards helping. But another thing to really remember about bond enthalpy is the fact that bond enthalpies are not totally accurate, and they're basically just they're like educated guesses based on the way that they're like rough averages based on what scientists think that the approximate enthalpy of each of those bonds is. But it can't really, it can depend on the molecule too. So it's kind of just it's really theoretical. It's not something that is directly applicable. But yeah, definitely I would focus on drawing the molecules if you can, and then really it's just endothermic is positive, exothermic is negative, and then you just take the bonds broken and then you subtract the bonds formed from that. So that's kind of a brief overview. Hopefully that wasn't too confusing, and I think I would look into each of the videos if you had anything that you're struggling with in particular. I covered the topics I think in depth in each of those videos. So yeah, I hope this helps.